Hello everyone, and this video I'm going to talk about example 5.7 or 5.11 textbook, and I found it's really kind of interesting. Okay, and then the statement of problem is like this: and then there's a guy trying to pull in a box on the surface, and he want to maintain constant velocity motion. Okay, he want to This guy want to pull in a box and also want to maintain a constant velocity motion. Constant velocity motion. And he want to ask, is there optimum angle? Okay. Is there an optimum angle? Optimum angle called theta. Okay. Okay, is there for doing this motion? Okay, the optimum means okay. So I should make it more clear. The optimum means the least effort. Okay, the least effort. So this guy want to pull in the box on the surface on the point on the surface, and also he want to maintain a constant velocity motion, and he want to ask, is there an optimum angle, or in another word, the least effort for doing this motion. Okay, so this problem is kind of interesting, so I want to share this problem to you. Okay, so yeah, the key for this problem is doing a constant velocity motion. Okay, constant velocity, that's very intuitively, or very intuitively, constant velocity means no acceleration. Okay, that's the key. Okay, constant velocity motion, that means there is no acceleration. Yeah, because acceleration is the change of a velocity, right? Regarding to the change of the velocity. But if the velocity is constant, there is no acceleration. Okay, so no acceleration in this the motion. So and next, let us do the force analysis on this box. Okay, so there is a force analysis of the box. Okay, so let's do the force analysis on this box. Okay, so this motion, there is no acceleration. So that means, well, so we can also use a component language. Okay, summation fx equal to max. So summation fy. So right now we just only two dimension. Okay, ignore the z direction. Okay, so it's may. So since this motion is constant velocity motion, so there is no acceleration. So that means your x component, the force x component of force, your net force x component of force is 0, and net y component of force is also 0. Okay, so let's do this. Okay, let's do so. Here is a tension. Okay, let's do the x direction first. Here, this is a tension. Okay, let's do the summation fx of tension, summation f of x. So tension is pointing to the right. Okay, and then tension can decompose to t sine theta and t cosine theta. And t cosine theta is pointing to the right direction, so it's positive. T cosine theta. Okay, is there any contribution to the x direction? Okay, yes, here is the friction between the box and the surface, and it points to the left direction, so it's a negative. Minus F kinetic friction. Okay, is there any x component any contribution for x component? I think no. Okay, so it's equal to 0. Okay, so let's do the stimulus in y direction. Y component, the tension can be decomposed to t sine theta here. So it's contribution to the y component. So it's point up, so it's positive. And also because this object is on the surface, so there is always a normal force, and normal force is point up, so it's positive and n. And is there any contribution in y direction? Yeah, here is weight of the box, so it's pointing down, so it's negative mg and equal to 0. Okay. So well, the question I want to ask is there is a least effort. Okay, the least effort means the least t. Okay, because this guy is pulling this box. Okay, by a rope. Okay, so if so, he want to find the least effort. So that means you want to find the least tension. Okay, the least tension. So is there any least tension or optimal angle for doing this motion? But we'll finally I will discuss this more. Okay. So let's make here we need to do a more algebra work. For example, we want to replace this. Okay, replace this the friction coefficient. Okay, the friction coefficient. The friction force. The friction force, like I say, is proportional to the normal force. Okay, the normal force times the kinetic friction coefficient. And what's the normal force? Okay. And what's the normal force? Okay, what's the normal force? Where we can get the information about normal force? Yeah, in this equation, we can get the normal force information from this equation. So here we can get the normal force equal to mg minus t sine theta. So if the friction force is equal to mu k and times mg minus t sine theta. Okay, so we put information back to this equation. So we will have t cosine theta minus mu k mg and plus mu k t sine theta equal to 0. Okay, and then we do a little algebra work. We go get a t cosine theta plus mu k sine theta equal to mg. So finally we'll get the tension. The expression of tension is mg over cosine theta plus mu k sine theta. Is that correct? Let me check the answer. Is that correct? Okay. Yeah, mu k mg. Oh, we missed mu k. Oh, yeah. So yeah, I missed mu k. Oh, okay. Mu k mg. Mu k mg and cosine theta plus mu k sine theta. Yeah, I forgot mg. Okay. So you can see your tension is a function of theta. Okay. Okay, why is that? Okay. So the problem is you want at least effort. That means we want to find the least tension, and also the tension is a function of the theta. That's an interesting problem. Okay, and let me explain this more detail. Okay, why is there an optimum tension? Okay, let's see. Okay, if the theta, okay, if the theta is higher, okay, if the theta is higher, let me see if the theta is larger. For example, theta is, if the tension has larger theta, that means if the tension is here, okay, if tension is here, which means large is theta, okay, and large theta it means you have large component on t sine theta, okay, large component of t sine theta, right? If theta is higher, you have large component on t sine theta, and t sine theta can reduce the friction. Why? Because let's see here. Okay, because friction is mu k times n, right? Mu k times n, And also your normal force is equal to mg minus t sine theta. Right? See here. See here. Your normal force equal to mg minus t sine theta. So if your theta is higher, that means you have larger t sine theta. So you have larger t sine theta, that means you have less normal force. Less normal force means less friction. Okay, so that's why if you have higher theta, large theta, that reduce the friction. But that doesn't mean the theta is as we want the theta as large as possible. No, because why? Because at the beginning the problem asks for he want to do the constant velocity motion. So you want to do the constant velocity motion, you need cosine theta. This one. You need cosine t cosine theta to make you maintain a constant velocity motion. So you see there's a two competition. In higher theta, large theta, yeah, you reduce the friction, but at the same time, you reduce the t cosine theta component. If you have a large theta, that means you have less t cosine theta component. Okay. So if you have less t cosine theta component, that means you have lower possibility to maintain a constant velocity motion. Okay, so it's two competition. Okay, large theta reduce the friction, but at the same time you cannot keep the constant velocity motion. So there is an optimum theta. There will be an optimum theta. Okay, there's optimum theta. So, okay, there's optimum theta. So we can use the calculation skill to find the optimum theta. But right now, I know you haven't familiar with the mathematical tool, so I just do it. I just do it here, and you just take it. Okay, you just take it. Okay. T is a function of theta. We do the derivative of tension with respect to theta. Okay, and we can get the equation like this, and we will finally find the optimum theta. Tangent theta, this optimum theta equal to this complicated formula. And we put a real some number in there. Let's assume the nu k is 0.6, g is 9.8, and mass is 10 kilogram. And then you put a number in, you will find there's the optimum theta is about 30 degrees. And you will also draw this graph in draw graphs by a computer program. So okay, yeah, your t is really a function of time, and there is the minimum, optimum, least tension in this problem. Okay. Okay, that's a very interesting problem. You higher the theta, yeah, you higher the theta, yeah, you reduce the friction. Yeah, that sounds you will have the least effort, but at the same time you want to keep the constant velocity motion. Yeah, so large theta doesn't allow you to keep the constant velocity motion. So there will be an optimum value for theta. So this problem is very interesting. Okay, so I want to share this to you. Okay, so I will start the video here, and hope you can handle this problem, and see you in the next video. Bye bye.